The topic: the treatment of industrial wastewater. That is, wastewater treatment, particularly industrial wastewater. Wastewater is any water that has been adversely contaminated by organic pollutants, bacteria, and microorganisms, industrial effluents, or any compound that deteriorated in its quality. Generally, the wastewater can be subdivided into two broad categories. They are municipal wastewater and industrial wastewater. Municipal wastewater is as a result of liquid waste discharged by domestic residences and commercial properties, whereas industrial wastewater is the liquid waste discharged by the industrial and agricultural activities. Some of the factors that might the composition of wastewater are land uses, groundwater levels, and the degree of separation between stormwater and sanitary waters. The composition of municipal wastewater is usually less variable than the industrial wastewater. The industrial wastewater being the highly affected by the type of industrial activity involved in that particular area where the discharge of effluent water occurs. Generally, the organic composition of wastewater is estimated to consist of 50% proteins, 40% carbohydrate, 10% fats and oils, and trace amounts of other pollutants. That is, other pollutants include surfactants and emerging contaminants. On the other hand, wastewater often contain 10⁵ to 10⁸ colony forming unit per ml of coliform organisms, 10⁻³ to 10⁴ colony forming unit per ml of facial streptococci, 10⁻⁰ to 10⁻³ protozoan cyst, and 10⁻⁻⁴ to 10⁻² virus particles. So, the wastewater should be, or industrial wastewater should be, treated before it is discharged into the atmosphere. The wastewater received from various sources are purified by a series of steps. The first step is called preliminary treatment, and the preliminary treatment removes squares and radially settleable inorganic solids with the size range of more than 0.01 nanometer. After this, there is the primary treatment, and the primary treatment removes the bulk of the separated solids, including both organic and inorganic matter, that is 0.1 to 35 micrometer. This is followed by the secondary biological treatment, and it is mainly used to degrade the biodegradable organic matter and nutrients present in this wastewater. After this, this is the final and last step is tertiary treatment, and it is used to remove a portion of the remaining organic and inorganic solids and pathogenic microorganisms through different processes. And this is followed by chemical disinfection. The primary and secondary treatment removes most of the organic waste, that is biological oxygen demand and suspended solids present in wastewater. However, up to the secondary level, the treatment of effluent water is insufficient to meet the quality criteria of drinking water or reusable for industrial or domestic recycle. So the effluent from a typical secondary treatment plant is still contain 20 to 40 milligram per liter of BOD, which may be objectionable in some streams. Therefore, in order to meet the quality of effluent provided by secondary treatment, it is essential to carry out some additional treatment, usually called a tertiary or advanced treatment. This is done to obtain high quality water as compared to that obtained from secondary treatment processes. The advanced treatment contains the unit operations not normally found in secondary treatment. Tertiary treatment removes the suspended solids, inorganics as well as organic dissolved substances and nutrients present in the polluted water. Several methods are used for this treatment. In our syllabus, we have to study only the following filtration and membrane techniques. That is, we have to study the filtration process. That is, filtration is generally carried out through the use of activated charcoal and synthetic ion exchange resins. That is, filtration process through activated carbon and synthetic ion exchange resin. And we have to study the membrane technique like reverse osmosis and electrodialysis. Let us discuss one by one. First one is the purification by filtration through activated charcoal. This method uses adsorption technique. Adsorption is a surface phenomenon and is based on the surface area available for the absorbing species. Charcoal is an amorphous form of carbon and is highly porous in nature. Its structure is close to that of graphite. It is in the form of a stack of plain layers of carbon atoms arranged in regular hexagons. Carbonaceous raw materials such as coal, lignite, wood, coconut shell, and some agricultural waste products and animal sources are the main sources of charcoal. Activated carbon is an effective absorbent because it is highly porous material and provides a large surface area to which the contaminants can absorb. It is prepared by subjecting charcoal to oxidizing stream at a high temperature of about 950 degrees centigrade. The activated charcoal is used both granular and powder form. They are called powder activated carbon PAC or granular activated carbon GAC. The water gas which is released from the charcoal is used to develop a very porous structure in the surface of the charcoal. Thus the adsorption process increases. Therefore, activated charcoal is capable of absorbing a wide variety of compounds when it becomes saturated with impurities. It is heated in vacuum at about 980 degree and the adsorbate are driven off. The adsorbent could be reused. That is, activated carbon can be prepared by using the reaction C plus H2O gives H2O plus CO. The water gas H2O plus CO that produced is get adsorbed on the surface of the charcoal. This activated form of carbon offers two advantages. Its large surface area is ideal to absorb pollutants and its redox potential is sufficiently low so as to reduce several metal ions to less toxic oxidation states. Nowadays, activated carbon finds wide applications in the treatment of wastewaters generated from industries such as food industry, textile industry, chemical industry, pharmaceutical industry, pesticides industry, and herbicides production and cook plants, nutrition factories, petroleum refineries and storage installation, organic pigments, dyes, mineral processing plants, insecticides, pesticides, resins, detergents, explosives, and steps. It is also employed in the treatment of sanitary and hazardous landfill leachates. And also, the activated carbon is used to remove impurities or isolates produced from wastewater stream by adsorption. The adsorption process can be described in 3 steps. That is, the process of treatment of wastewater using activated carbon involves 3 steps. First 3 steps. Initially, a liquid or gas contacts the activated carbon particles. The impurities in the bulk liquid come into contact with the external surface of the carbon particles. Next, the adsorbates diffuse into the internal pore structure of the activated carbon. The final step is relatively fast and it involves the attraction of the adsorbate to the surface of the pore walls, where the chemical or electrostatic forces which are hold them. The type of force that holds the adsorbed molecule on the surface has a considerable effect on certain characteristics, in particular how tightly the molecules are held and whether the solid will absorb certain substances more strongly than the other. In industrial wastewater treatment, activated carbon adsorption can be utilized in the tertiary or advanced level treatment steps subsequent to biological treatment for the removal of refractory organics. To some extent, this procedure may be effective in the removal of inorganic materials also. Next, we have to discuss the purification of wastewater, industrial wastewater through ion exchange resins. Ion exchange technique is used to remove metals which cause hardness to water, especially manganese and iron containing salts. Ion exchange generally consists of a cation exchanger coupled with an anion exchanger. Ion exchange resins are cross-linked long-chain organic polymers with microporous structures. The ion exchange properties of an ion exchanger depends on the functional group attached to the chain. Water is first passed through the cation exchanger, which are capable of exchanging its H plus ions with cations of the impure water and the acidic resins containing basic groups, especially NH2 and OH group, which are capable of exchanging their anions with the anions of the impure water. That is, resin SO3H plus M plus gives resin SO3M plus H plus, and also resin NO3 OH minus plus X minus, that gives resin N plus X minus plus OH minus. That is, here the H plus and OH minus again are regenerated, is reacted to form pure water molecule. The overall outcome is the removal of cationic and anionic impurities present in the water, and we get the resultant demineralized water. This figure shows a schematic diagram of anion exchange processes of of the purification of industrial wastewater. Both the type of resins, that is cation and anion exchange resins, are easily regenerated. Cation exchange resins are regenerated by passing a dilute solution of HCl through them. On the other hand, anion exchange resins are regenerated by passing a dilute solution of sodium hydroxide through them. The advantage of ion exchange process is that it is highly acidic or alkaline, whether alkaline water can be treated by this process, and this process removes the hardness of water. Next, we have to discuss the purification of or the treatment of industrial wastewater through reverse osmosis. Reverse osmosis is the process of the reverse of the osmosis process, and it is used to remove the dissolved impurities like salts from industrial wastewater, and this has become more popular at homes for water purification. The reverse osmosis results in the reduction of concentration of the dissolved solids, including a variety of ions, metals, and suspended particles such as asbestos. Osmosis is a natural process. It involves the flow of solvent from a less concentrated solution or a pure liquid into a more concentrated solution across a semi-permeable membrane. The pressure which is exerted by the solvent as it passes through the semi-permeable membrane is known as the osmotic pressure. On contrary, reverse osmosis is the reverse of osmosis. Here the direction of flow of the solvent or water is from the high concentrated solution, that is impure solution water, to low concentration solution, that is pure water. To carry out the reverse osmosis process, the pressures we have to apply the pressure, that is we have to apply the pressure in the opposite side as that of the osmosis. The contaminated water is placed above the semi-permeable membrane and is subjected to high pressures. Pure water flows down the semi-permeable membrane and dilute and the solute molecules, that is it mainly include the impurities which are larger than the pore size of the membrane, are retained by the membrane. And normally the pressure applied to the reverse osmosis is several orders of magnitude greater than that of the osmotic pressure. The following figure 2a and 2b shows the process of osmosis and reverse osmosis respectively. This process, osmotic pressure process, that is RO process, is effective in the removal of particles of size ranges from 10⁻⁻⁴ to 10⁻⁻² micrometer, and its operation efficient with an efficiency greater than 90%. These two figures are the phenomenon of osmosis and the phenomenon of reverse osmosis. In osmosis, particles are moved from high concentrated side to low concentrated side, whereas in reverse osmosis, the particles are moved from low concentrated side to high concentrated side. The membranes used in reverse osmosis process are effectively non-porous and significantly reduce total dissolved solids, heavy metals, organic pollutants, viruses, bacteria, and other dissolved contaminants. But there is a limit to which the mechanical pressure that can be applied to the solution. The reverse osmosis process are operated at pressures ranging from 75 to 250 psi. In some cases, high pressures tend to tear the semi-permeable membrane, which are used in the reverse osmosis process. The materials, so care should be taken in that cases. The materials most commonly used for the filtration purposes are cellulose acetate, cellulose butyrate, and polyamide. That is, in RO processes, the semi-permeable membranes are made up from cellulose acetate, cellulose butyrate, and some sort of polyamides. An RO membrane can typically produce 10⁻⁻35 gallons of water per day, and it depends on several factors including membrane type and operating conditions and the degree of impurity in wastewater. Next, we have to study the purification of wastewater, industrial wastewater, using the phenomenon of electrodialysis. Electrodialysis is basically an electrochemical process. It involves the migration of ions through ion selective semi-permeable membrane. Electrodialysis is a membrane desalination process and uses electric current for the passage of water molecule across the membrane. It is an efficient method for the removal and concentrating this water. The process is based on the principle that the dissolved salts, impurities which are either positively or negatively charged, and these positively and negatively charged dissolved salts or impurities migrate to oppositively charged electrodes when it is subjected to an electric field. Therefore, the electrodialysis processes uses two types of ion selective membranes. That is, cation membrane, which allows the transfer of cations only, and also anion membrane, which allows the transfer of only the anions. The following figure represents the working of an electrodialysis cell. Here there is two electrodes, one positively charged electrode and a negatively charged electrode, cathode and anion, and two semi-permeable membrane. As I said earlier, it is positively charged and negatively charged, cationic and anionic membrane. Generally, a typical electrodialysis system consists of an electrolytic cell divided into three compartments using two semi-permeable membranes. Parallel channels are constructed by alternating membranes, that is cationic and anionic, between the electron. On passage of electric current through the wastewater or saline water, the negatively charged ions migrate to the anode and positively charged ion migrate to cathode. Therefore, the solution in the alternative channel are likely to become more concentrated, and in the remaining portion it become more dilute. That is, in the remaining portion it become ion-free pure water. Using the electrodialysis method, around 50% to 94% of the dissolved solids are removed from wastewater, which containing 12,000 milligram per liter of total dissolved solids. The limitation of electrodialysis is that it cannot be used effectively for the removal of organic molecules because as they are larger in size than inorganic molecules, they get coagulated or clogged in the tiny pores of the semi-permeable membrane. Another drawback is that it requires high energy for desalination of the concentrated feed solutions. Some references: EPG Pathshala, a gateway to all postgraduate courses, and Environmental Chemistry Fundamentals, Georgi I. Ibanez,